Isothermic, isobaric, isochoric, and adiabatic?
Yep.
Mm-hmm.
Okay, so who wants to tell me what an adiabatic process is? Other than Russ. You always ask. I'll call names one at a time. Adiabatic process.
That's the one where everything's
Nicole.
changing?
No. Well, could be, but there's fundamentally something about adiabatic process.
No heat can get in or out.
No heat can get in or out. It's a thermally isolated process, no heat exchange, typically really fast. Happens faster than thermal conductivity can occur. Okay. Or convection, radiation. Okay, isochoric. We have, who wants to take that new table? Q, Ivan, Marco. Gotta know these. I mean, there's just no messing around with this stuff. What do you think? Isochoric, what is it?
Isochoric. I'm just gonna take a shot at the dark at that. I'm assuming
It's
either.
not baric, it's not thermal, it's
Right.
not heat exchange, only one thing left, right?
Okay, so it can't be pressure.
Sometimes called
Can't be
isovolume.
temperature. It must
Oh.
be volume constant. Okay, so
Constant
volume's
volume. What does
constant.
constant volume imply in any system?
Well, constant volume
What do you
is
think?
there's no work.
Total work
Oh.
is zero, thank you.
Okay, thanks. Thanks everyone.
Okay, so isothermic or isothermal process, what do you think? Guys, feel free to answer that one over at that table. Ian,
Where the temperature doesn't change.
any implications of that? These are big.
There's no change in internal energy.
What else?
Heat equals work.
Good man. So, isobaric. What do you think, Elizabeth? Trying to put you guys on the spot, but we just need to think about these. We just gotta be intrinsically aware of what they are. You know the difference between a sentence and a paragraph. These are key.
Constant pressure.
We've already talked volume, temperature, heat, what's left?
Pressure.
Pressure. So what's the implication of a isobaric process? Well, lots of things, but one of the most important is that temperature and volume are both capable of changing, requiring a net transfer of heat. To that end, when energy is absorbed, it's partitioned. Some of it results in temperature change, some of it results in work or volumetric expansion. These are always sort of interrelated. Well, the nice thing about covering the thermodynamic processes and the ideal gas law and its implications in a way sort of so quickly is that when we talk about how they integrate and how they form cyclical or cycle processes, the nice thing is you end up using them anyway, so you can almost start with chapter 20 and then just sort of introduce the terms or the ideas as you're going along, because you end up having to use it in application regardless. And it's not always easy, certainly. But what I want to do, first of all, is sort of lay out the basic idea of thermodynamics as a whole, and the basic ideas associated with thermodynamics. I'm just going to lay them out, and then we're going to talk about how we use them. So to begin with, there are four really canonical thermodynamic equations, or laws, excuse me. And they have a very interesting structure. Now, part of the reason for the way they're defined is that we sort of got to the end, and then to make it mathematically like a proof, had to go back to the beginning and add one, because it was kind of missing but inferred. So, to begin with, there's what we call the zeroth law of thermodynamics. This is sort of the but really it allows us to make an assumption about something that we sort of tend to overlook. And the idea is if you put two systems in thermal contact and allow them to do their thing when they reach thermal equilibrium. If you take one of those systems and put it in a location where it can be thermally interacting with a second system, if the system is at the same temperature as the first system at thermodynamic equilibrium, that means it's in thermodynamic equilibrium in the second system. So now, that's the long sort of description, but basically what it comes down to is that if you measure temperature with a thermometer, and you put the thermometer in another system, if it's at the same temperature, you're going to measure it and have the same value. It's basically a way of saying thermodynamic heat transfer processes have a definable, measurable temperature, and you can use a reference standard in order to measure that temperature. You don't have to assume that if you take a thermometer and stick it in one system and get some value, if you put it in another, at another temperature in another system, if you measure the same value, you can assume that they're at the same temperature. So it is sort of stating the obvious, but it is sort of a relevant thing. Easiest way to say it is that two systems I'll say in thermodynamic equilibrium at the same corresponding temperature. And it's come back around to our idea of the second law of thermodynamics. The extension of that is that if then one of these two systems is in thermodynamic equilibrium with a third system, simultaneously, same time, the third system is also in thermodynamic equilibrium with the first one. Or would be if they were in turn interfaced or interacting. So about that two ends. In other words, if you measure the temperature of one system and you measure the temperature of another system, if they both represent a thermodynamic equilibrium state, it means they're in the same temperature. In other words, basically you can physically measure temperature and it has a quantitative meaning. Believe it or not, that's sort of what it all comes down to. Okay, the second law of thermodynamic, or first law, excuse me, the second in order, which was really the start, is another way of saying conservation of energy. Energy conservation in thermodynamic processes, or in thermodynamic systems. And by conserved, I mean accounted for. In other words, to put it in an equation, and we sort of started doing this, thinking about it just purely from energy flow on Thursday. But the idea is is that when a system absorbs energy, if you will, in the form of heat, dq, then that energy absorbed, dq, will be essentially distributed in one of two ways. Well, unless we are accounting for more processes. And we're sticking with non-chemical processes for now. That energy will either result in a change in internal energy, or some of it, or all of it, in some cases, will be related to some sort of a change or a corresponding amount of work associated with the system. In other words, the system, if it absorbs energy, will expand. If it releases energy, it may contract. This work is the work by the system, very important. When we think of this from a technology or a utility standpoint. Something absorbs energy, maybe it expands, that expansion can result in the system performing work on its environment. Yes, Russ?
Well, actually, I guess the way I saw this in the book is the same statement, because it was E equals Q minus W.
Yeah,
But
but
that-
think of it always in terms of the heat flow, the energy flow into or out of. It is the same thing.
Yeah,
Um,
but that's the thing what you're saying is by the system is important, because if it was on the system, then it would be the opposite. Correct.
Now, the way we define the internal energy, how do you know when the internal energy of a system changes? Temperature changes. If it's closed and you're not gaining or losing mass or particles, gas, if you will, if the temperature changes, the internal energy is changing. We started that by establishing that when you look at the temperature of a system, it in fact scales with the average internal energy of the particles in the system anyway. So if there's a change in one, there's a concomitant change in the other. So another way of saying this is if you have a system of n particles, throw a Boltzmann constant in there, there will be a corresponding temperature change associated with the internal energy change. Now, this process, I'm just going to move 1/2 over here. Distributes for all the individual particles involved. Okay, so when the temperature changes, if you have one particle, hypothetically, two particles, the energy associated with changing the temperature, you can think of it as the change in internal energy of one particle times the number of particles that are there, if you will. The whole thing is the pizza, if you will. But we've got to think about how that energy is spread out. I don't know if we talked about this or not. Okay. At least in a gas system, in solid systems, you're sort of limited sometimes by how things can move around. But in gas systems, if you take a gas particle, how many different ways can this gas system physically, or this gas particle, physically move?
Translational?
Well, translational, but when we say translational, what do we mean? It can move left or right, it can move up or down, and it can move forward or backwards. And it can do any of these three, or all of these three, simultaneously. That's why we need 3 dimensions to describe a position and a velocity vector if we're not reducing it to a 2-dimensional quantity. So there are, in fact, from a translational perspective, and I'll try to draw this this in and out of the board. So there's going to be a right angle between all of these things. Each individual mode of motion, independent, any we call it degree of freedom, or any specific translational motion that can happen that is independent of any other possibility, okay, left, right, up, down, forward, backwards, has an average energy each of these, I'll say 1, 2, 3 modes of translation. Each of these modes of motion has an average energy of 1/2 kT. Now, if it's a gas that is just sort of randomly, things are all moving around, that means on average, you've got this amount of energy in each of these 3 simultaneously, because one is no more likely to happen than any other. And so on average, it may be going forward faster sometimes, and not going up and down. Sometimes it may be going back and forth. Whatever it's doing, on average, every possible way it can move has this amount of average energy. Okay? Now, if you got 10 particles, you multiply this number by 10 times the number of freedom degrees, or the number of degrees of freedom. Now, I forget how I always forget what letter I use to describe it in the notes. But, so I don't mean to give you different letters. I've been spinning all week, so I've had crazy meetings. But let's just make one note that I'm going to call it CDEG. In other words, this number represents, I guess I don't want to use N because I don't want to confuse it with N for number of particles. But the number of degrees of freedom has 3 translational simultaneous values, or 3 possibilities, 3 different modes. And this is for translation. Now, point particles. The assumption is all the mass is at the center. There's no rotational motion associated with something that has 0 radius. Because if there's something has a 0 radius, in other words, it's condensed to a single point in space, there's no associated rotational energy. But for any system that has an effective span in space, then you have the possibility of rotational motion, and therefore rotational energy associated as well. So there are 3 modes of translation, and this is it for a single monoatomic gas particle. We just treat everything like a little tiny little ball or speck, and they're all moving around. This is what you get. So this is for a monoatomic ideal gas. In other words, the internal energy, the total internal energy of the system, with some number of n particles, will be equal to this C over 2 quantity. Again, temperature in Kelvin times the number of particles that are physically there. In other words, average internal energy times the number of them there, which would correspond to 3/2, if you will, NKT. We'll remind ourselves that these are Kelvin quantities. Okay. The next level of complexity of a gas particle is essentially a diatomic particle, or a particle where you have basically 2 atoms attached at the hip or joined by a single interaction. This is called a diatomic. particle. And pretty much any particle that has a linear symmetry like this, for instance, 3 atoms, like carbon dioxide, that are attached in a long pellet sort of shape, would be the same. You would apply the same idea. But when you have a system like this, you can also have simultaneously 2 rotational modes of motion. This system can rotate in the plane and simultaneously rotate in the vertical plane, or I mean in the horizontal plane. Okay, so you take a gas particle, it can rotate this way, and it can rotate this way, I guess. As I've got this set up, I've got it back this way. So it can rotate this way, and it can rotate this way, and they can happen simultaneously. So we got 2 more degrees of motion. And they're independent of each other, just like projectile motion. We only dealt with rotation in 1 dimension, or 1 mode, but there are 2 possibilities. So we now have 2 more modes of motion when you have a slightly more complicated system or gas particle. Now, it cannot rotate along the 3rd axis because the assumption is it's a point particle along that 3rd axial direction, so there's no associated energy with this. Only with this, and only with this, not this way. Okay. Again, 0 radius along that axis. If it were crooked, now we'd have to deal with potentially additional complications. And really, really hot systems is another possibility you may think of right off the top of your head. Vibration, just like, remember, harmonic oscillation. There's also other possibilities as well, but we're not going there. We're going to ignore that extra complication. So, when you have a diatomic system, a system of diatomic particles, then the number of degrees of freedom is now 5. 3 translation, 2 rotation, in which case the average internal energy, or the internal energy, the total internal energy of the system, is going to be the sum of the number of particles times 5 halves kT. Again, each mode of motion has, on average, 1/2 kT energy. Okay. So we sort of define the Boltzmann constant, so that's the case. System absorbs energy, you can measure the temperature change and the energy absorbed if nothing else is happening, and you can correlate to some Boltzmann constant. And we did that with the ideal gas law separately anyway. So there are ways to get what this corresponding value ought to be. But in either case, what it means for us, coming all the way back over here, is that we have to include another term to describe how much average energy per state of motion times the number of motions that are equally probable at any given time times the number of particles that are present, that are all doing this. Okay. Crowd noise. Basically crowd noise. And then we add to that what we ostensibly already are familiar with, calculation of work, which is the pressure of that system times the change in volume. Pressure doesn't have to be constant, it just has to be expressible in terms of volume, as the volume itself is changing. Because there's always a pressure-volume interplay. This is tough. This is Newton's second law for thermodynamics. This is a tough system to solve in some cases, easier in others. But everything usually in a thermodynamic process comes down to calculating or solving this system. Okay? So this is the hard part, always. And then everything else is sort of a consequence when you put these guys together. Does that make sense? It's kind of deep, it looks okay on the surface, start thinking about it, it kind of makes your mind spin a little bit. And I don't know to what degree you've done this before. Okay, so let me get rid of this. By the way, did he talk in terms of Boltzmann constants or in terms of the ideal gas law and Moy?
So,
Both. I'm going to talk about everything in terms of the Boltzmann constant. The numbers are less friendly, but they're more direct and meaningful. You think in terms of what's physically happening. I'll leave it to your responsibility if you want to think about it in terms of moles to be able to make that transition in your mind. We don't have time, among other things, to go back and forth too much. Okay? So hopefully when you put together your study notes and for your process that you were comfortable going one direction or the other. Okay. I'm not going to make it so that it's a big, spurious selection of all kinds of things just to throw you guys off, per se. I just think it's easier to talk in terms of what's happening to one and then how many you got. Okay, so to add to this, then we have the second law of thermodynamics, which is, I could spend an hour talking about the second law of thermodynamics in various ways. But think about the second law of thermodynamics. This we've basically seen before. Maybe not in this form, this is energy conservation, right?
yeah.
The second law of thermodynamics is probably the least, you ask somebody with a physics degree or a chemistry degree what the second law of thermodynamics is, and an engineer in most cases, they'll give you the classical definition, but not really tell you what it is or what it means, okay? In a real, tangible sense. They kind of know what it means. But I want to lay it out. So the idea of the second law of thermodynamics is essentially, and this is the most important way to think about it, heat only flows from hot to cold, and never backwards when you have a thermodynamic, when you have an energy or heat transfer. Okay? Energy only flows one way, hot to cold. Any circumstance. We can fake it and we can trick nature to work around that, but that's the direction it goes. So, and we normally say spontaneously, because if you look from the outside, you can fake a system and create something like a refrigeration device. But even then, heat is physically, at any given point, only flowing from hot to cold. Now, the way we deal with that, or the way we justify it on a classical state, or in a classical way, is to say that the reason this happens is that nature tends toward always the most probable state. Okay? What's most likely. Don't think about this in any esoteric way if you don't have to. What's the most possible way? I take 3 pins, and 4 pins, and throw them up in the air. How are they going to land? Well, they're going to land in the way that's most probable most of the time. If I do that 10 times, 100 times, I might be able to get them to do something like this. Throw them up in the air and up. Of course, these won't stand on end, but hypothetically, they could all stand like this. There's a problem with that. It's not very probable. It's not very likely. Not going to happen over large quantities of simultaneous events. Okay. So, in a sense, what that means is that the most probable state, or we could summarize the most probable state, is a state where they're all basically about the same. They're all doing more or less the same. When you're in this state, you've got things aligned in very specific ways, in a very specific pattern. Everything is in its proper or accurately, precisely defined place or state. Everything is about the same state now, it's just all over the place. So the idea in nature is that we typically say that the transition of processes that happen naturally always tend towards sort of a uniform, scattered, random state. And I'll say flow, but I don't necessarily mean flow, I mean tend to, something happens, it just kind of goes. We call this property of randomness or relative randomness, call it entropy. Not chaotic, but random. Call it a chaotic process. Or I'm sorry, a random process. So the obvious example, if you take a hot cup of coffee, hot water, add an ice cube. The ice cube is highly ordered. The distinction between hot water and cold, solid, ordered ice are very well specified. Either in the solid or in the cold, depending, or the liquid, depending on where you are, but you can define them with a certain amount of precision. But over time, what happens? The random bumping around of the hot water ultimately warms up and then melts the ice. And as this continues to happen, on average, the energy becomes more and more spread out and more uniform. And pretty soon you cannot distinguish, given enough time, here from here, other than spatial location, or maybe pressure because of the fluid depth. But in a big sense, all of the particles ultimately just sort of randomize out and become about of equal temperature and equal energy. Happens on its own. You can't take hot water and somehow miraculously get ice cubes. Now you could take some of the hot water, go through a very complicated process and freeze it, but that doesn't happen on its own. Right? Rooms get messy on their own over time. It requires a lot of diligence and extra effort to straighten it up. Right? Your clothes get dirty and they become uniformly filthy. Given enough time, whatever you're doing, when you want to clean them and get things nice and neat and straight, you've got to put a lot of time in. You've got to wash them, maybe dust them off, wash them, dry them, iron them, whatever you do. You've got to go through a lot of effort to get it nice, ordered, an ordered state out. But really what it comes down to is heat flows from hot to cold, because high energy systems, when a fast car hits a slow car speeds up, fast car slows down. Ultimately, they get closer to each other. Kind of cool when you think about it. That's the idea of the second law of thermodynamics. But it allows us to say whenever you look at a system, you know at all times what direction the heat's flowing. You never have to worry about some opposing opportunity. Only goes one way. Funny thing is, 8 years of higher education, I never once thought about it that way. I kind of knew it, but I never actually thought about it that way. They asked me what the second law of thermodynamics was. I said, well, you take a closed system, and in any given process, the entropy is either not going to change or it's always going to increase. Well, what's entropy? What's random? Well, that means I can draw it out, I can write an equation, but it doesn't really say anything. This is really the consequence of the second law of thermodynamics. And this is what constrains and what defines the requirements for any process that uses heat energy transfer to proceed. So to this end, we have this concept called entropy. Entropy. And entropy has a very specific Measurable is relative. It's not the same thing as. It's relative disorder or randomness. Not how randomness changes, it's just the relative randomness of a system. So you can compare the entropy of one system with the entropy of another system. And it turns out, because heat only flows one way, entropy changes in a system. When that system absorbs energy in the form of heat, right, you get all this random collisions happening. But it's inversely related to the temperature of that system. This here now becomes a very esoteric relationship, but every once in a while it becomes useful. But very briefly, I'll point something out here. If you rearrange this in terms of heat, you could say something else too. You could say that dQ is related to temperature times change in entropy. No entropy change, no heat flow. Another way of looking at it. Since work associated with any volumetric change of a system is related to pressure times change in volume, you may note that we can now express this entire first law of thermodynamics in terms of a quantity and a differential quantity simultaneously. I'm not sure how meaningful that needs to be for you, per se, so trying to lay out what these things mean. But what it does mean is that we can now express the second law of thermodynamics, the first law of thermodynamics, and I am going to re-express it now in a way that you might prefer, the way Phil probably runs it. We can say that the internal energy change, whatever it is, how a system's energy changes by temperature, will depend on the heat flow in minus how much work that system performs at the same time that process is happening. Ever eat a bunch of carbohydrates, like a big thing of spaghetti, and you get really, really hot? All that energy basically has no place to go other than just it increases your metabolism and makes you sweat. It may make you tired, and your body's trying to store all this energy to do something with it. But if you eat a bunch of carbs and actually go out and do something, then that energy gets sort of displaced and spread out. Some of it ultimately is, you've got this transference to internal energy, but you take away the mechanical work that your system ends up doing along the way. I should have wrote this way, didn't write that yet. Jumping the gun. But this ends up being expressible as this. And I point this out for a couple reasons. The first reason is in an engineering thermodynamics class down the road, you may be very likely, and it depends on how the paradigm of engineering thermodynamics is changing in terms of the way it's taught. But you're very, very likely, highly likely to see it in this form. This is the only way I ever saw it, in terms of the calculatable expression. So just kind of be in mind that you'll see this form. And there's a certain, by the way, there's a certain symmetry again. You've got this state variable and then this changing variable as the state variable, as this product defines heat flow, and same with work, even if they're interrelated. But this is, again, kind of like the zeroth law, if you will. If we're doing some physicists, we want to put things in a very clean little symmetric package. You can have a particle, you should have an antiparticle. So it's sort of one way of defining what this might look like, and then ultimately what does it mean? Well, then you can go through all kinds of interpretation.
Also, if you're using that expression, you have to have some kind of quantity for ds, for change in entropy, right? How the
You
heck
either have
would
to
you
have a
come
way
up
of
with that?
solving it, or you can calculate ds by looking how a system changes and selectively dispersing or selectively applying the first law, the ideal gas law. And we'll come back to that one, but I want to now shift gears here because I want to put all of this into its proper place. But before I do that, I got to add two other things, or I got to add one other thing, excuse me. There's one other thermodynamic law. And again, this is one of those why? Not quite sure, but it is fundamentally important at a basic level. Third law of thermodynamics. And by the way, this is a consequence of the first law, the second law, and the zeroth law. Is that we define temperature, since temperature is, as we define it, proportional to internal energy, random kinetic energy, then we can say that there is a asymptotic limit in nature that a system can, or to how cold a system can get. So, absolute 0 Kelvin, or 0 Kelvin if you will, is the hypothetically lowest achievable temperature. Now I say hypothetically, but the reality is when systems get cold, what happens? The disparity between that system's temperature and its environment becomes greater and greater and greater, which increases the probability of energy to flow in and ultimately randomness to continue to be generated. So you can never actually reach this absolute zero because of the heat transfer that is inferred from the second law. You can't isolate a system at 0 Kelvin unless its environment is also at 0 Kelvin, which requires that that second layer of environment has to be ultimately isolated from its outer layer, because otherwise heat's going to flow into that, which is going to flow in, and it's always a cascade inward to the lowest temperature. So in other words, it defines absolute zero, kind of like the speed of light. It is nature's speed limit for temperature. Nature's fundamentally never achievable, but hypothetically possible, lowest temperature. And by the way, we've gotten close. Here's a trivia question for your next cocktail party. Where is the coldest location in the universe?
Wherever is the furthest place from anything.
Where is the coldest temperature, measurable temperature in the universe? Only happens once in a while.
I would say
Deep space?
Deep space is about 3 Kelvin. And we know that because we can measure the radiant spectrum, apply the Stefan Boltzmann constant. So we can see what the temperature is. And it seems to get, 3 to Kelvin, 2 to 3 Kelvin. No, it isn't colder than that.
so are you talking about like observable? Like with
Well, measurable. In other words,
Measurable.
we've measured it somewhere. We've physically seen it. We know where it is sometime.
Place of very low pressure.
Well, that's a
Extreme.
requirement.
oh, yeah.
No.
Vacuum,
Well,
extreme
if
vacuum.
space is a vacuum, then you've got zero pressure there.
I'm assuming a black hole
But
of
you've
some
got zero
sort.
anything, including substances.
Right.
So there's no definable temperature. You need more than one particle to have a temperature in the first place. Right? Because it's an average, the average of one. And there's no such thing as rest anyway, right?
I think I could travel in time in that place. I think.
No, this is the trick. It's at some lab in Germany,
Well,
Max
right.
Planck Institute. They've managed to achieve a system of particles down to about 3 billionths of a Kelvin.
That's ridiculous.
That's as close as we've seen to get so far. Remember that fourth state of matter, the Bose-Einstein state? You need to be down around a billionth of a Kelvin in order to get it, because it's so unstable. Any small energy absorbed knocks it right back out of that ordered state. So, just give or take, it's probably changed by now, but it's about 10 to the negative 9th Kelvin. It was at one point achieved in Colorado, in Boulder, Bureau of Standards and Measurements, but I think they've recently gotten it even lower. Germany. So it's kind of a trick question, but it's the truth. It's,
Yeah, I remember reading somewhere, and I don't know if this is right or wrong, but that part of why you can't achieve absolute zero is because you'd have to have zero volume. Is that true, or is that not true?
Never really thought of it that way, so I won't address that without thinking about it, because I've never thought of it that way.
Volume in
You
terms
need
of
zero
is the
motion.
right place. It is the right
You need
place.
zero pressure. You have to have something in there. So, I don't know.
Actually,
That's cool. That might be another one of those Degrassi discussions.
Oh,
Shows up. Neil deGrasse, is that Neil deGrasse?
it's DeGrasse.
It's
Neil
grass,
deGrasse.
okay, whatever, it's all grass anyway, right? Grass is always greener. All right, so these define everything. So we approach any problem. If there's any conflict of these